feature class.
And then we go underground.
Exactly. And I want to discuss today and prove Margulies superutility. So I want to explain this. So take theorem. I will discuss it in a special case, which I will do. Take let gamma in essence real be a lattice. Let G be a K simple adjoint. Adjoint means no center. So it's an algebraic group, which is semi-simple, in fact simple. This means that actually it's simple as an absolute group, if it's simple as a joint. Where K is a complete field with an absolute value. So in this setting, I'm rather specific on the gamma and its host, the enveloping simple group, and quite general about G. This is like S, I'll call it in the future. Assume Rho is a map from gamma to G so this is an algebraic representation of this gamma. And so I forget about this. I'm having a data, an algebraic representation of gamma alone. I want to assume this is dense, and the image is unbounded. Then O extends to S. That is, we have the following diagram. Gamma is in S, we have this map to G, and we have unique extensions under minor assumptions on this form. We call it Oba. So this diagram is what you need to remember. This is the famous Margulies superutility. He has various corollaries that we could discuss in later underground classes. And more general formulation. So we place S by say some adjective connected, simply connected, semi-simple group. So connected, we all know what it means. Simply connected, it's not topological, adjective, it's about the algebraic group structure. So it's like SL is connected while PSL is not. This is an adjoint form. So among all forms of the semi-simple group are related by, how much of the center are there, is there. Simply connected has the most center that you can have, and adjoint has the minimal amount, etc. I will not get into it now. So replace S by a simply connected semi-simple group over a local field in our
connectedness in the Hausdorff topology is just, I mean, if ROC. If you feel this is the PID, just to make sure that everyone understands it. The Hausdorff topology, the non-algebraic, the analytic topology, is totally disconnected. So all these terms are actually linears. Over R or C, those terms has their meaning in the algebraic form, and also they have the meaning in the non-algebraic, but maybe an example that will illustrate differences, take SL2R. This is connected as an algebraic group, but it is not connected, simply connected. Also connected, of course, but it is simply connected as an algebraic group, but it is far from being connected, still simply connected as a topological group, and in fact it has a Z cover, which is, it's called SL2 tilde, right? It's coming from the topological type, homotopy type of SL2R is the same as of SO2. And so pi 1 of SL2R, I'm taking SL2 here because this is striking, is isomorphic to Z, or isomorphic to pi 1 of SO2, which is isomorphic to Z. And we may extend SL2R, this is a general part, by this. And this is the group we will get, or the SL2R tilde, is a simply connected topological group, which is of course a Z extension of SL2R, but it is not an algebraic group. You cannot present it as matrix.
In the other direction, if the R group is simply connected in a topological sense.
If a Lie group is simply connected in topological sense, then it is simply connected also in the algebraic sense. Otherwise, you will have a cover in the algebraic sense, which also will be a cover in the algebraic sense, which is nonsense. And we talk about the rings here. So I can replace this by any group over a local field here. Here I'm a bit more generous about the field that I'm allowing. Just should be a valid field. And then, but if S is not simple, but just semi-simple, then I want to assume something more about gamma. Assume gamma is irreducible. Again, for those who haven't seen this before. Of course, there is a higher rank. So this is not about higher rank. Rank is about the rank of the group is the dimension of a maximal torus defined over the field, the local field in this case. For SL2R, the rank is 1. For SL3R, the rank is 2. Higher means 2 or higher in this case. So this theorem fails for SL2R. It will also fail for obvious reasons if you take SL2R times SL2R, and your lattice gamma will be a product of lattices in both factors. Then you will have a failure, but by the same reasons, basically, you can just project into one of the factors and complete diagram. So you need some irreducibility assumption, and again, I'm not going into it, this is just a so this is basically what I want to prove in this class, but observe. But now I want to make an observation. We may set, now let's take this S and think about it, S is real, and think about it as a space. When denoting it as X, this is what I do, set X to be the Lebesgue space obtained SO3, I'm having the R measure on it, and I'm thinking of it as a base space, forgetting the group structure, but in a minute I will recall it. Gamma act on it by left multiplication. For T, say, being that unit of the group, or actually any other, we may also consider the right multiplication action of T on X, which commutes with gamma. Yeah, I'm saying trivial things, but there is a reason that I want to somehow, in the data I'm given, I'm having only data about gamma, and somehow I don't want to, I don't know S as a group. Yeah. Okay, I think things with my motivation of setting this setting will be clear in the future, but now, so the observation is, observe, gamma times T on X is ergodic. Moreover, in fact, so gamma times T on X, basically it means that if I take X, I'll mod out T, and I let gamma act on that one, this is ergodic. This is the ergodicity of that action is the same as the ergodicity of this action. But actually, if I take, sorry, I wanted to advance the course. Is ergodic for every so we actually prove this one. This follows from what? Our previous discussion of method ergodicity, or also known as weak mixing in this context. That here we have a probability measure presenting. Here we have a probability measure which is preserved under the S action, in particular under the T action, and we've seen that obviously this is S ergodic. The S left action is ergodic, is transitive, so it is ergodic for every power by metric ergodicity theorem that we proved, and this also restricts to the T action. So we have this X, this is the bi-action of gamma and T. And actually, T, I could have replaced T by many friends that it has. I mean, by the choice of T that I took was quite arbitrary here. We call it T12 if you wish. And now, so motivated by the fact that we have this place X and this bi-action which has this kind of ergodicity, I'm going back to what we discussed in the last lecture, which was the category of representations of bi-actions. So let me remind you this. So
last time I was discussing, I was defining the category and I was making a term which I haven't yet proved. Representations by actions. So I will remind you the setting, I will remind you the term, I will prove it, but it is a fairly abstract term by itself, but we have a major example that fits into this picture. So maybe we should have this one in mind. So assume X is by action of gamma times t. Now, in my mind now I'm freeing myself from this specific situation. This is all I'm concerned about, but somehow it is easier for me to speak abstractly. Assume having z-dense unbounded gamma to G algebraic. So a representation of, well, of X, actually a representation of all these data, I'm reminding you, is a map X to V. This is a variety, and here I'm having the gamma times T action. Here I should have G times L action, so I have the color to emphasize the thing that I'm choosing, and I was not given before. So L is a new thing, V is a new thing, and those things vary, and then I should have a map here. And here I'm semi-choosing this arrow also. This should be rho times a new map theta from T to L. And we discuss lengthily the notion of morphisms of such things. I will not repeat the definition. I will now state the theorem that we mentioned, that assuming what we observed there, that the T action on X mod gamma to the N is ergodic for every N, this category then has an initial object. Of the form well, so it should be a map from X to some G mod H. So this would be an homogeneous G space. But of course, there should be an L action on it as well, where, well, maybe end. So before expressing this, let me recall. So there should be some L acting on this space, commuting with the G action. The automorphism of a coset space commuting with G action is always of an action on the right, but not any element. If I would have G here, what commute with the left action is the right action. And elements of G that actually preserve the factorization by H are just elements of the normalizer of H. So those are exactly the elements that can act on the right. Among them, H, which is a normal subgroup the normalizer of H, act trivially. So so L is a subgroup of the normalizer of H, normalizer in G of H, model H. So this is obviously an algebraic subgroup, an algebraic group by itself, by its own light. And of course, we should have some map that I call it from T to that L. So the claim is that there exists such data which serves as an initial object. So a priori it was not clear, it is not clear that we have an initial object at all for this category. And particularly, it has this special form, it is homogeneous. So what is an initial object? Just I'll express it in a diagram, just to recall basically the definition of a morphism. This means that whenever we have a morphism to whatever guy V, so I will have a morphism to G mod H, this is given, this is my, maybe this is phi naught. Whenever we have some phi, we will have a unique subthing. But there's a lot of decorations of these diagrams which I will try to record. So there is this G model, maybe I should call it, I should denote things here by note. And if I forget, just to emphasize, this is the initial thing. And this is G times L, and here we have gamma times T, and we have up here, and up there. Everything should be equivariant with respect to these maps. And also that this N and L node should be related by some, I don't know, N prime that goes here in the, and there should be a map from T. Okay, we see what's going on. So I need to give you that. And I know how I want to proceed and give you this. So this theorem is, again, is correct. The theorem that I'm about to prove, like this is an initial object, is correct in that generality. And it is mostly interesting in this example that I just erased. But I will prove that one. How does one go about? So consider for a minute X or maybe let's make an observation. Or lemma. It's the same lemma that we had before. Just forget all about forget this initial object. Just take for any morphism or for any representation, sorry, X to V with all the decoration which I'm lazy to put. There exists some G mod H, sorry, a priori G times L. So this comes with an L. And this is some orbit. And is a subgroup of G times L. And this is the injection of an orbit inside V. And I claim that the lemma here says that whenever you represent X into V, you hit one orbit. And this lemma follows, basically we've done it. For what? What is the who's and who's?
Yes, you have Z dance.
Sorry?
S, X, and X.
No, S. No, no S, no.
Oh, sorry.
Great. So who does act on X? Gamma and T. Gamma and T, and my assumption is that this is the very strong erodicity assumption that put the box here. This implies, this is the case n equals 1, that T act ergodically on X mod gamma is ergodic, which is the same as T times gamma act ergodically on X, right? So the case n equals 1 in this assumption guarantees the ergodicity of gamma times T on X. Now I'm pushing this to V. V is some G L space, or G times L space. Now forget all the categorical nonsense that we have. There is some L which was chosen here when I decided to discuss this particular V. There is an L, G times L act on it, and it has this group. Forget this is important. This group has a nice orbit structure on V. This ergodic measure, gamma times T ergodic measure, must be pushed into 1 G times L orbit. And this is it. This is the content of this lemma. It's the same lemma that we've done before, just obscuring it with many extra data which is irrelevant for us. I guess, okay. I'm not sure what part of the, okay. I don't know. Part of the discussing, I rate that one. Now, I haven't used so far the extra ergodicity assumption that I did assume. Without it, this term would not be correct, wouldn't be correct. So I need to assume this, and it comes, so maybe I haven't finished the lemma yet, because this is just an explanation of the first step of it. This is part of the lemma. We have such that G acts transitively on G times L mod n. This is the actual important part of the lemma. So the fact that X will hit one orbit, and it of course will be of the form G times L mod n, is more or less a triviality, or triviality given what we achieved so far. But under this stronger ergodicity assumption, not only G times L, but actually G itself will act transitively on that orbit, on that specific orbit, not okay. So why? This is what I want to prove. Consider maybe let's take this and divide by G. So what will we get? We'll get an L space. Consider the L space L modulo, so M is a subgroup of G times L, so project it to L, maybe. This is the projection of M to L. By the way, we're discussing algebraic groups here. The projection, the image of a homomorphism of an algebraic group into another algebraic group is always closed. In general, I cannot just take a group in G times L, project it to one of the factors, and expect this to be closed. But this is closed. So algebraic groups, this is an algebraic groups, an algebraic subgroup of M, and this is an L variety. And the map
we add x to g times L mod n. This is basically this is dividing by g. I'm getting map to L P2M. So I'm having a map from x here. And since it is g invariant, this map will be invariant with respect to who is that one which I have to remember. No, T went.
So gamma.
Yeah, T went to L. Gamma went. Sorry for. I'm keeping erasing the data, but as both room is limited. Gamma went to G. When I divided the G action here, actually I could have divided by. I guess I should have written the gamma action on the left. All along I failed to do this. But, this must factor from here. Right? So forget the upper half of the diagram. Just take this thing. Look at that. This here reflects to this I don't know, psi map representation. This is a representation of the L space, sorry, the T space, x mod gamma, T still acts on x mod gamma, and it is a representation of this guy into an L variety via the algebraic representation of T. So if you fix the group L and the homomorphism from T to L, I may consider all representation of the guy x mod gamma, as we have done before. But x mod gamma is extremely theoretical. And we've seen before what?
The gate is point.
What?
The gate is point.
The gate is a point. That the gate of such is a point. Which means that image L mod P to N is a trivial L space. Okay, so this means that G was acting already transitively here. When I took the G orbit, I got nothing. Which means G on G times L mod N is transitive. This is the end of the proof of the lemma. So the theorem says that there exists an initial object which is geohomogeneous. The lemma that we have proven, and I guess I erased it by now, the lemma says that for every object, for every representation, I can, from every representation, I can kind of pull an orbit. This is not yet known to be an initial element, this orbit, but this is just a geohomogeneous friend in it. Okay? But now, having this, I can continue and prove the theorem as I had before, as I did before. And now I do the theorem. Consider the connection
So basically, I will look at all candidates of such things. Yes.
Why should the L model of the projection be a point?
Okay. So L mod. So I'm looking at this green box here, and view this as a representation with respect to this map. I'm having this algebraic map, T to L. Forget about gamma, forget about. Okay. You got it? Or should I continue?
Yes, if you
Yes.
can.
Yes.
If you may.
So this is a T space, this is a T ergodic space, moreover, with a lot of ergodicity in it. This is an L variety. And I consider this representation, but I know that the gate of, I know that there should be, okay,
Like graded size image is 1 point, but why does this mean that?
okay, so maybe this, so inside there is a 1 point image, okay, I should have said this. And I guess it's a very good question, and I haven't said a certain word today, which I did say last time, but I should have said, which explains this. So the image in it is a point which is T invariant. So this is a T invariant in that N variety, and T is the risky dance in N. Okay, this is by assumption, and this assumption I didn't see. Also, this, by assumptions, whenever the L that serves me in the definitions is always the closure of the image of T. So this point here is L dense, is L invariant in that L homogeneous variety. So this variety is. Thanks for asking this. So where am I? I want to prove the existence of an initial object. By now I know that for picking an arbitrary object, I can find in it something of that form, not yet known to be initial, need not be initial in general. But now I can focus on the collection of things of that form. Consider the collection, well, A, G, and G, so this is something that we had before, such that there exists right, X, so this G mod H, and of course gamma, T here, and G, and L should be here. So I can such take a complete data in this form. L surely could be assumed to be inside the normalizer of H over H. H is some cool acting. So I'm looking at that collection. Before I knew that G act transitively on this, I could have looked at the collection of all M's. This would be my first try, maybe. But this collection wouldn't be bounded, as I have no bounded L. L varies. But G is fixed in my game here. G is fixed. So this collection is some fixed collection of an algebraic varieties inside this algebraic variety G. Of course, G algebraic. H and T. This subgroup. So Nether gives me a minimal object. So by now I'm kind of using that lemma that I expressed. I'm able to interact to the proof that you may remember of a similar thing, but less complicated. Not the category of actions, not of bi-actions. But again, for this we needed that solvency assumption. First, to exist H0 in that collection, which is minimal with respect to inclusion. So So we pick that H0 and we pick along with it all the decoration that are supposed to be there. So this is a matter of choice. Everything here is a choice, but H0 should be minimum. Pick. So X, call it P0 now. We made a choice of L0 here. And that guy all times theta 0. So this is the object that we will argue to be initial. And again, maybe write down another diagram as this one, reminding us modeled over a diagram that we previously have written. Actually, it wasn't the end of the semester and things probably are fading in some of your minds. I would ask you to know everything by yourself. So assume we have a representation V of X. So I'm adding a representation of X to V. Sorry. Adding here V. This is the representation. I'm adding phi. And I'm having G mod H naught here. And I'm having that representation. Phi naught. I'm asking, can I construct that guy over here? This is the same diagram as we see here. And here's the way I'm doing it. I'm taking the product as before, G times H0, and the projection. And there are things there are decorations. Maybe I will not write everything because then the diagram will be extremely complicated, but I'll say it. Along this map is equivalent with respect to some G times L action. This map is equivalent with respect to some G times L0 action, which I picked on the board on the left. Here, what is the group that act here? G, of course. And L times L0 act on this committing with G. G act diagonally here. L act committing with G on V. L0 act committingly on that guy. And we have the map theta times theta 0 from T to this thing. I'm not done yet, because now this need not be Zariski dense. So I'm taking the Zariski closure of this map theta times theta 0 into L times L0. This will be the L group that acts here. Obviously it is mapped into L and L0 in a compatible way. So I want to claim that I can define the extra structure that is needed to be defined in order to make this map over here a representation. When I draw this arrow, it's not just a map from X. In my mind, I'm having some extra structure here. Shall I be explicit about it? Shall I write it down? So let me write this one. So here I'm having L. Maybe I'll emphasize that just this one. L0, and I'm having T maps here. T maps here. This is theta. The guy comes with the structure of V. This is theta 0. And here I will have, first approximation, I will have L times L0, and I will have the product map, theta times theta 0. This does not satisfy the axioms that you've seen I was using a minute ago, of the risky density, but this is not a problem. I can take this L prime, which is the closure of theta times theta 0 of T inside that product space. And from this guy, or actually from this, I'm having the well-defined map here and there, and they are well-defined on L prime as well, of course, in that state. And everything commutes and everything is fine. And now I'm using the lemma. The lemma told me, actually I was a bit careless later on, earlier on. Okay, so the lemma tells me that I'm having such a sub-representation. Which I can define in a G times L fashion, or G times L prime. Actually, when I proved the lemma, I didn't care about L. Oh, sorry, no, this is just fine. Okay, I'm good. And, okay, you know what comes next. So I'm looking at this map over here. I'm saying that this is a morphism of representations. And this contradicts the choice of H0. Or it does, given the choice of H0 or choice of minimality, I'm saying that this must be an isomorphism. And this isomorphism then must be expressed by a map in the other direction, of course. Yeah, here there is a delicate issue. I don't know how much should I emphasize it. The L here that I chose was minimal. That is, it was chosen inside a normalizer. Of course, I could inflate it in some arbitrary form. I can take the product of this with an arbitrary group or something like that, and let some other guy act, and may view this as my initial object. So now, what I want to say that maybe there was an issue that I discussed in the definition of a morphism, this L prime issue that maybe should be used here. I will not stress it further, but think of it maybe later on. But now we see that I can take this road here, and this is a representation of that space. And by this we prove this existence over here, and uniqueness somehow is.
So by minimality, you want to argue that L0 is isomorphic to L prime. Is that right?
So what do you mean? No, L prime is something maybe.
You also want a map from L0 to L.
So
and you want to argue that
so
L0.
strictly speaking, I may not have a map from L0 to L. Actually, I gave you an example at the end of the last lecture. I mean, after the end of the last lecture. But this is exactly why I will not have strictly a map from L0 to L, but after inflating L will, maybe.
Okay, so then why did you mention this, the minimal choice of L0? I thought it was for this.
Because this is why I'm choosing. I want to choose my L0. I can choose it to be such a minimal form, and I do.
But where does it figure in the proof? That
No. It's an extra info that the proofs gives me.
Okay.
Maybe, I mean, just by construction, maybe I get. I can make my initial object with that L.
No, it's hard to keep this category in mind, but somehow the uniqueness up to isomorphism in this category of biorepresentation does not give you that the L0 is unique.
Yes.
Somehow a little strange.
take gamma to be the trivial group, take T to be unknown, some non-trivial group, maybe Z, acting on a point. Okay? Just I'm now coming with an example explaining why things are going on. What will be the initial object associated with this? Okay, and now take G to be the trivial group, and take the trivial homomorphism from gamma, which is a trivial group, to G, which is a trivial group. Here I am giving you
The most non-trivial now in this.
T.
No, I lost it. Okay.
T was non-trivial. It's acting trivially on a point. Everything is trivial now. So what will be the initial object of yours? It will be some G mod, well, it will be a point acted upon by G trivially on one side and by some L on the other side. This L could be the trivial group, and I will map T to it trivially. This L could be, say I'm walking over the rings, it could be R, act trivially, and Z is mapped into R in the usual way. And as elements in this category, these two things are isomorphic, because I'm able to inflate by this. So this is triviality, but yeah, so we have many are on the L level somehow, we have a lot of isomorphisms. So I choose somehow the minimal L that can serve. But there is a matter of choice here, just the natural choice to make. What is time? Full time. So just let's guarantee that I'm done with this. Yeah, so we proved that term, and after lunch we will see how we can use that term, which is some general notion term in some very complicated category, to prove something which is non-trivial.